Today's lesson is on section 7.1, solving linear systems by graphing. During chapter 7, we're going to learn a few different methods to solve linear systems, but I think this is the best one to start with and the best one to really show students and help them understand what's going on when we're trying to solve a linear system. As I've got up here, and I want you to write down if you're taking notes along with me, a linear system is a set of two or more linear equations in the same variables, so talking about the same x and y, or so whatever variables it happens to be, but usually we use x and y. So we're talking about these two equations right here. And when they're in a system, we're talking about those two equations together. We've dealt with the equations separately by themselves and being able to graph them and find their solutions. But now if we're saying that these two equations are in a system, what we're looking for is the solutions that fit both those equations at the exact same time. So again, there are an infinite amount of solutions for this first equation, and we can sometimes graph that and show all those solutions. There's an infinite amount of equations for the second equation as well. But now we're looking for solutions that fit both of those equations. And what will happen is sometimes there's only one of those answers. Sometimes there's only one solution. Sometimes there's an infinite amount of solutions. Or sometimes there's no solution at all. What are these solutions going to look like? Well, it's usually going to be like some ordered pair, like a point. We're talking about x and y. So we need values for x and y that work in both equations. So something like this, like an ordered pair, like maybe 3, 4. And I'm just kind of making that number up. I don't think that's actually the solution of the system. If I plugged in 3 for x and 4 for y in each of those equations, it wouldn't work. So, but just for example, we're looking for some kind of ordered pair, some kind of point, a solution to that system. Again, graphing is the first method we're going to use to solve systems like this. I think it is the best way to understand or help students understand what's really going on. We're looking for one particular point, or maybe there's a case where there's no solutions or infinitely many solutions. I think by graphing, sometimes it's easy to understand why it works out that way. By working with the equations, we can see which type of situation we have. And so graphing, I think, is the best way to start. It's the best visual way to see what we're really doing when we're solving a linear system. Here's just a very simple, very brief example of a problem where you might use a linear system to solve it and to find the answer. This is a very, very basic word problem. It says you and your sister are saving money. You currently have $10 in your piggy bank, and your sister has $2. Each week you get $1 for doing your chores, and your sister gets $2. Maybe she does more chores. After how many weeks will your sister have as much money as you? So this first equation we could say is your equation, how much money you're going to earn as time goes on. So y is how much money you have. X is the number of weeks. And again, you only get $1 per week, so not much of an allowance for you this time. So, but we'll use that as just kind of a basic example. And then we'll say that your sister gets $2 per week. And right now she has $2 in her piggy bank. When we're going to graph a linear system, all that happens is we just graph both of those equations on the same graph. And we'll see if we see something interesting or what happens with those lines when they cross paths. We'll talk about that here. But so we'll just start graphing a linear system. It's almost just a review of graphing. So this first equation, y equals x plus 10, I could say, well, my slope is 1, my y-intercept is 10. So if I go up 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, put a point, and then my slope is up 1 over 1, I can make a bunch of points, and here's how much money I would have as time goes on. Getting $1 every week and saving that dollar, there's how much money would be in my piggy bank. Well, my sister, again, she starts off with $2 and then gets $2 also every week. So her y-intercept, I should make these first, her slope is 2, her y-intercept is also 2. So she starts at $2 and then goes up 2 over 1, assuming she's saving each of those dollars each week. How much money is in her piggy bank? Here would be the graph of her equation. As we can see, again, hers is increasing a little faster because she's getting $2 per week, so it catches up, in a sense, to mine. And at one particular point, these 2 points actually intersect. Or these two lines, these two equations, intersect. This is the solution to our linear system. This is the point we're looking for when we graph. Because what the blue line represents is all the money I have as weeks go on. Well, in this case, it's like all the solutions that work for my equation. So after so many weeks, here's how much money I have. For my sister, same kind of thing. It's saying how much money she has after every particular week. And at what week do they finally meet up? Do we actually have the same amount of money? Well, it looks like it's this week right here. If I count it over, 1, 2, 3, 4, 5, 6, 7, 8. After 8 weeks, that's where we'll have the same amount of money. When we're doing linear systems, again, sometimes we'll have a word problem, sometimes not. But where those lines cross, that's the solution for the system. It's the one point that works for both equations. Again, the blue line, for just being an equation, this represents all the solutions for that first equation. The green line represents all the solutions for the green equation. So where they cross is a point there's a solution to both of those equations at the same time. So that's why that's the solution to our system. In this case, it looks like, I think it ends up being about 8. And then if I go up 11, 12, 13, 14, 15, 16, 17, 18. If I follow this over, this is at 18. So this is the point 8, 18. After 8 weeks, we'll each have $18 for this particular word problem. But more importantly, just showing you here's a situation where you could use a linear system to solve a problem, or a situation we might use for word problems like this. For just any kind of basic problem we might be solving, again, whether it's a word problem or not, again, let's say the problem says solve this system by graphing. So just like we did with that first example, I'm just going to graph both these equations on the grid and try to find out where the point where they intersect is. That would be the solution to this system. So let's say I'm going to graph this first one in red here, y equals 2x plus 4, so kind of like I did on the previous page. I'll say my slope is 2, my y-intercept is 4. My y-intercept's 4, I go up 4 on the y-axis. I go up 2 over 1, up 2 over 1. When you're solving these systems, I would recommend making a lot more points than you usually do. One, that'll keep your line a lot straighter. And again, obviously, if we're trying to graph these really well to find one particular point, you do need a nice straight line so you can make sure you have the correct line and it's going through the correct points. Also, if you make a lot of points, sometimes one of those points ends up being the solution, so that might make it easier for you to find as well. Graphing this other equation, y equals negative x minus 2. The slope of this one is negative 1. You notice there's no number in front of there. It's like a 1, so negative 1. And the y-intercept is negative 2. So I'm going to go down 2 on the y-axis. And I'm going to go down 1 over 1, down 1 over 1. And if I reverse direction, as you can see here, I end up plotting that point that I plotted earlier in the red line. So there is an exact point where these two lines intersect. Here it is. And that point looks to be negative 2, 0. So that would be the solution to this system. One other way to check and make sure that that is the solution to this system, if it's a solution to both equations, like we talked about in the beginning, then that means it should fit for both equations, right? Negative 2, 0 should work in this equation and it should work in that one. And that would prove that it is the solution to the system because it works for both equations at the same time. If I plug negative 2 into this first one, it's kind of maybe showing that work up here. If I plug 0 in for y, I'd have 0 equals 2 times negative 2 would be negative 4 plus 4. Well, negative 4 plus 4 is 0, so yeah, that does check out. So that makes the equation true. Negative 2, 0 is a solution for that first equation. Checking the second one down here. 0 equals, well, negative 2 times negative 1 would be 2 minus 2. Is 2 minus 2 0? Yes, it is. So yes, that solution, negative 2, 0, works in the equation, works in both of the equations. So yeah, that must be the solution to the system. If you're a person who likes step-by-step directions to kind of help you, here's the steps I would ask you to use while you're solving equations. Or sorry, while you're solving linear systems and finding the solution to the linear system. Step 1, just like we did above, we're going to graph both equations on the same grid. So again, that's almost just like a review of graphing. Step 2, find the point where the two lines intersect. That's going to be the solution we're looking for. Many systems are going to have one solution like that. We'll talk about some special cases in the future where, again, there can be no solutions. There are infinitely many, but usually we'll be looking for the one solution. And then 3, check a point, as I did there in the black writing. check a point to see or check that point to see if it works in both of the equations, so that I know that's the correct solution to the inequality, or to the linear system. And again, this is the kind of work I would look for as well. If you're wondering what to show, here's exactly what I would look for. Just kind of plugging those numbers in and seeing what you get on each side of the equation and checking to see does that work or not. If your point didn't work in one of the equations, and that's why I asked the class too, what would that mean? Well, that means maybe you didn't graph the problem, one of the equations correctly. So maybe one of them was just a little bit off, and that threw your point off, and then it's a solution to one of them, but not both of them. Well, then maybe you have to recheck your lines and regraph them. Or maybe you just misspotted which ordered pair you were looking for. Maybe you said -3, 0, and like we have here, it should be -2, 0. So just be careful when you're graphing. And that's why we do need nice straight lines, and that's why you do need to put a lot of points to help yourself make the correct graph. But if you check that ordered pair in both those equations, it should work. That'll tell you if it's the solution to the system. Go through one more example here of solving a linear system. In this one, the two equations are in standard form, so we're going to graph them using the intercepts method. I think that'd be the easiest way to graph these two equations. And even using that method, it should still work out. I should still be able to find the point where the two lines intersect, and then see what the solution to this system is. So I'm using the intercepts method. Remember, what I do is I plug in 0 for x, plug in 0 for y. I do that each separately. When I plug in 0 for x, it's like it cancels that term out. So that's gone. So all I have left now is 2y equals 10. And if I solve that little equation, I get y equals 5. So I can find one of my intercepts very quickly using this method. If I plug in 0 for y, that will cancel out this term, and all I'll be left with is x equals 10. So that must be my x-intercept, 10, 0. So again, using that method, if you're still kind of struggling with it, I would like you to keep practicing it, because that can be a very handy method to graph equations. So let's see, 0, 5 is my y-intercept, 10, 0 is my x-intercept. So this equation would look something like this. Then the second equation, I'm going to use intercepts for this one as well. This one I'll just do all red. And again, there are those steps if that helps you. Graph both equations on the same grid. I'm doing that right now. I'm graphing the second one. If I put in 0 for x, that cancels this term out, so I have -2y is equal to 6 left. Divide both sides by -2, I get -3 for my y-intercept. Going back to the original problem, if I put in 0 for y, I get 3x equals 6, so I get x equals 2, so my x-intercept is 2, 0. So 0, -3, 2, 0. There's what my 2 points would look like. Here's the graph of my equation. And now again, what I'm looking for is that point of intersection. So I'm looking for where the two lines intersect. It looks like I do have a nice point right here. It looks like that's the point 4, 3. So hopefully that is the solution of the equation. I picked out a nice problem here. It has a good solution, numbers that I can plug in very easily. Again, the last part, part 3, still very important. So I've graphed both equations. I think I've got a pretty good solution there. But the third thing I do want you to do is check and see, is that point the correct solution for both equations? And again, in terms of work, just a small amount of work is showing that, okay, I plugged each one in and it works for both. So if I put 4 in for x, I get 4 plus, and then 3 in for y. 2 times 3 gives me 6. Does that equal 10? Yes, it does. If I put it in, that's putting it in the top equation. If I substitute it into the bottom equation, 4 times 3 gives me 12. 2 times 3 gives me 6. 12 minus 6, is that 6? Yes, it is. So 4, 3 must be the solution to that system.